Hi, I'm Kristen Grauman. This is work about sights and sounds in 3D spaces. Here we're talking about agents in 3D environments who have multimodal perception. The first part of this talk is about audiovisual navigation, and this is a project done with all the collaborators you see here, both at Facebook and UT Austin. First, to set the stage, there is an increasing amount of work in embodied AI for visual navigation, where an agent must use its egocentric visual stream in order to intelligently move around and explore a new place that hasn't been mapped before. And we've seen a lot of very exciting work in the community happening around this challenge. Problems like visual navigation and visual exploration, where you can have systems learning from the bottom up, even how to map the space and how to encode not just where things are, but also semantics that help an agent intelligently move. Now, at the same time, there's a salient missing ingredient for these agents. They live in silent environments and they are deaf. And so this is the thing that I want to zero in on in this work, looking at how to instead consider the world as an audiovisual place for our agents, and in particular in the context of navigation. So why do we want to do this? What will sound inform our agents about? There are a number of different important things that we can expect. One, it will allow an agent to hear something that is itself the target. For example, the phone ringing in another room, or the baby crying, or some window breaking. This is something the agent should be able to move to even though it can't see it yet. There's also possibilities for safety, like places that should be avoided based on the sounds that are coming from them, or other dynamic object occurrences. Furthermore, we have semantics in sound. If the agent at the bottom of this scene were to hear water running from a given direction, that's a sign about what possible objects or scenes or rooms might be there. And finally, sound gives us information about geometry and materials. So knowing what we can hear and understanding the link to spatial characteristics of the environment gives us a richer perception for this audiovisual observation. So I am going to touch on a few of these cases in this talk today, and starting with the one of AudioGoal. This is where, say, there's the phone ringing in another room and the agent needs to navigate to it. And what's really important to notice about this challenge is that the audio is going to allow us to sense the target before we can actually see it. For example, here on the right, if the phone is near that couch and the agent is down outside of both of those rooms, but can sense the sound intensity coming and bleeding through the doorway, this will be a signal that we should be able to learn to send the agent to the proper place. Now, this is the first time to our knowledge that this problem has been tackled for agents working in photorealistic environments with 3D settings and real sound. So to do this, we first needed to establish an audio simulation platform. We want to be able to hear proper sounds for our agent as a function of the geometry and materials of the environment. So to do this, we started with the publicly available replica environments, like one that you see here, and we used an audio ray tracing approach in order to render and pre-compute the sounds for all parts of this environment. In particular, you store the room impulse response for every source and receiver coupling of locations. And that's what these yellow positions are here in this environment, places at which there would be room impulse responses measured. Now this RIR is the transfer function saying how sound is transferred from the source to the receiver as a function of the geometry, as a function of their relative separation, and a function of the materials in the space. Now, once we have these functions, we can convolve with the appropriate one in order to hear the agent sound at any given position for any given source. So for example, here, if the source was at that red hotspot, then the agent would receive the appropriate binaural sound when we pull it from the given receiver location anywhere else. Okay, so this is a general rendering of the sounds now computed for all. Now let's look at the task. Here I'm going to play a video and we're going to hear the sound and see what the agent sees on the left-hand view. The top-down map in the center, not available to the agent, but it will start to discover it as it moves. There's a phone ringing, it's coming from another room, and the agent's job is to go find it. And you can see as the trajectory goes that the agent could tell as it exited that first room that it wasn't in that direction. And then as it moves down closer, it'll start to hear that the phone is getting louder, and furthermore that it's coming from the left side. Now keep in mind, to hear this, you'd need to listen to our original video with headphones. And so then it approaches the target and it reaches it and stops. This is the task of audiovisual navigation: find the sound source and use both sight and sound to navigate to it. So the first model that we propose to tackle this problem takes a reinforcement learning-based approach in which we'll learn a policy for how the agent needs to move given what it's hearing and seeing from these multimodal inputs. And this framework is very much related to others that are now common for treating purely visual navigation. And it looks like this. So we have as input the visual stream, and then we also have, in our case, this audio stream, which is coming as input in terms of two spectrograms, one for the left ear, one for the right ear, and optionally there will be GPS sensing. Now the multimodal inputs are aggregated over time with this sequential model, and we use an actor-critic approach for learning this policy in order to generate actions that the agent will take. And these are actions in the space of move forward, turn left, turn right, stop. Okay, and having sampled an action, then this loops back because the environment changes, the agent sees and hears something different as a function of its movement. And what it'll learn is, by us rewarding it for navigating quickly to the target, it will learn a policy to use all these cues in order to find this sounding object. Now, importantly, we consider both the case with all three of these modalities, as well as the case where, in fact, the task is simply audio goal, meaning there's no pointer at the onset, like in the so-called point goal task, telling us where the target is. And I'll come back to that in the results. So first, let's look at what the audio features learned within this model have captured. These are T-SNE plots showing projections in 2D down from the CNN encodings that were learned for those spectrograms. And on the left, they're color-coded according to the distance to goal, and on the right, they're color-coded according to the angle to goal, which of course is not directly known by the agent, but what we see here is that, as exhibited by the clustering of similar colors, meaning similar distances or angles in these plots, that the features learned have managed to capture this automatically. Now, what about actually executing on some episodes of navigation? Here, I'll first show you an example, and then we'll look at some numbers. So here is a baseline. This is a point goal agent that does not have a sound, and is trying to navigate to the target, which is yellow on the bottom of the screen, using just vision as well as GPS. And what happened in this particular case is, though, while there is a shortest path there in pink that would require going outside the door and then around to the other room, the agent ran out of time in this episode, kind of stumbling around at that bottom mid wall. And that's because the point goal signal from the onset was telling it very strongly to go in that direction to get to the yellow target. And this will give you the kind of success rates you see here. This is the success rate normalized by path length, or FPL, the common metric for navigation, and higher is better. Now, if instead we use our agent and treat this as the audio point goal problem, where we do get that pointer towards the goal in this case, but we also can hear that sounding target, we get a much closer path to the shortest path. And the numbers as well go up significantly. So this is great news, as we would hope once we are incorporating audio into the framework as part of the sensing to find this goal, the accuracy of the navigation is much better. The next thing I want to show you, we think, is even more than that. So here, when we treat this task of point goal or audio point goal, we're saying that at the onset, the agent has a vector telling it where is the goal. And this is very commonly the way the task is posed in the navigation literature today. However, we also know that having that information is extra, right? And furthermore, if we rely so much on that information to get us there in combination with a GPS sensor, we'll be in trouble if the GPS is not perfect. And so what this chart does is look at success rate on the vertical axis as a function of adding more and more noise to the GPS sensing. And first of all, what you see here is the good news that because our agent with audio can still hear, even in the presence of noisier GPS, its accuracy rate stays relatively stable as that GPS gets noisier. So this is important. Furthermore, if we think about the task, which is audio goal, meaning we do not get that displacement vector at the onset telling us where is the goal, then in this different task, we can still be completely immune to any problems with GPS. In fact, we're not using it. Right? So the agent is able to find its way to the goal at a steady accuracy rate without needing this direct pointer to it. And I think this is an important suggestion about where audio can play a role for this real-world task of moving towards sounding objects. And by the way, even if we do add noise to the audio stream, we're seeing relative robustness to that. Now, in every case, the environment that the agent sees during navigation is new. Now, we're also interested in seeing what happens if the sounds are new. So this is a set of experiments where from left to right, we made more and more challenging sounds in terms of whether the agent had heard them during training or not. And the short story is that if GPS is also available, the performance is quite stable with respect to unheard sounds. If it's not, it does get more challenging. And I think we can improve these quite a bit once we're training on a much wider array of sounds. Now, the model doesn't always work, of course, and some of the failures we notice are things like you see here, where the agent may start oscillating around an obstacle or choose a path that is kind of a long way around it. And we can attribute this to a couple things about the current model. One, this action space is very step-by-step, and so there's a lack of abstraction or sort of myopic choices are being made. That's hard to do in a very long string of actions. And secondly, we have a memory that's rather simplistic so far, simply aggregating state through this GRU. So, in our next steps in this research, we've looked at how to overcome these limitations and really enhance the model that we're putting forth to do audiovisual navigation. And there's two important things in this new model. So in this picture, on the right-hand side, you can see occupancy map, acoustic map. Now these are new grounded spatial representations that we add to the model beyond what I was showing before, which is the egocentric view and RGB or the binaural audio spectrograms. And this will give us a multimodal spatial memory in which we record as the agent moves in this space, both where obstacles are in its occupancy map, but also the history of what it's heard as it was moving in different positions, what we call the acoustic map. So that's the one key new ingredient that we want to explore. And the other that we propose is audiovisual waypoints. So we'll make this architecture more modular so that we're not confined to these step-by-step actions of the agent as before, but instead the agent can set for itself waypoints that it should travel to with, in our case then, a planner to get to each intermediate point. Okay, so we're going to learn audiovisual waypoints and we're going to incorporate an acoustic memory to make this model much richer. So let me show you what the model looks like then. Now we have as input the RGBD, so here we'll take the depth image, project down to the ground plane so that as we accumulate these observations from the egocentric view, we get more and more of the occupancy map filled in. Secondly, we have the audio input, and now rather than only using those raw spectrograms for learning that you see on the left, we'll also have this spatially grounded acoustic map, which in this case is encoding the audio intensity at the egocentric positions and accumulating those over time in concert with the occupancy map. Then we'll have this important module which does the audiovisual waypoint prediction. And so now this policy is generating the waypoint. Okay, so given the maps that it's discovered so far, as well as the raw visual and audio inputs, it will select for itself a subgoal. And if intuitively, as some of my images before showed, audio is strong as a subgoal creator because, again, before we get to see something, we can hear it coming from certain directions, which suggests the kind of intermediate goals that might be useful to set. So in fact, we're going to learn to set these goals end-to-end within the navigation policy itself, or for the navigation task. And so having selected a waypoint, then the inner module of the system will plan a path given the partial map that's been reconstructed so far by the agent in order to meet and find that waypoint. Then the environment will update and the agent will see something new, hear something new, and this process continues. So the key new ideas in terms of the technical approach here is first that we're inferring sub-goals via the policy. And we think that this is new with or without the context of audio-visual. Traditionally, sub-goals are set in this navigation space based on intersecting the intended goal with the frontier of exploration, or by learning to map to shortest path waypoints. And instead, we're letting the policy learn to set these goals. And then the second key idea is the acoustic memory. Right, so let's look at what this, how this looks and sounds for an agent now, exploring another space. And when I play this, again, the goal is in the red, the agent's this blue arrow, and as we go, it'll set waypoints for itself in yellow, and the purple will illustrate the acoustic memory. So let's play this example. So it's starting to record its audio history in the acoustic memory. The yellow is the waypoint that it's setting for itself next. Phone is getting louder, the new waypoint set near that doorway. Enter the correct room, it's louder, the waypoints are getting closer. Okay, and then once the waypoint gives back a delta x, delta y, that's 0, 0, the agent will know it has reached, believe it has reached the goal, and will issue the stop action. So this was just one sample showing the agent at work leveraging this grounded, spatially grounded acoustic memory together with its ability to set waypoints on its own directly in concert with this navigation text. And we found quite good results when doing this. So here I'm reporting results on those same replica environments from before. And here are an array of metrics. SPL is the first column there. The others are success rate, normalized distance to goal, the number of actions, and the success rate weighted by the number of actions. And our results for our full model is shown here, highlighted in yellow, whereas the model of the previous version of our method that I described earlier is shown here in blue. You can see right away these new additions of automatically learned waypoints as well as the richer acoustic memory are responsible for a big jump in the success rate and the SPL. Furthermore, there's also some concurrent work coming at ICRA 2020 from Gan and colleagues where the audio and the visual streams are treated separately, and the audio gives a beacon from which to predict the final goal location, and then the visual stream is used to navigate and plan to it. And we're seeing good results with respect to both these existing methods. Furthermore, you can see the impact of the acoustic memory in the ablation on the bottom, where the model here, ours AV-WAN, without the acoustic map, AT, loses about 4 points in SPL. Now, to give a qualitative sense of what these agents are doing, the three I was highlighting on the previous slide, we can see example trajectories here. Now, remember that each of these agents has no pointer to the goal. They do have clean odometry, but there's no pointer given to know where the goal is. And we see on the left, with Ganna and colleagues' approach, there's quite a challenge because the method requires predicting where the final goal location is based on audio and then navigating to it with the visual map. But this, because of the difficulty of finding that final goal prediction correctly, there's a lot of backtracking. In the middle, our previous model with pure RL and the step-by-step actions is better, but still doing some unnecessary motions thanks to that more myopic view of the action space. And then finally, the current model I've just described with waypoints is getting a much more efficient path on the right. All right, so I've been talking about this problem of audiovisual navigation with a target location, the ringing phone. And now I want to shift to an example from our work trying to tackle the use of audio in a 3D space for semantics and geometry. And for this, we'll introduce our work on VisualEchoes. This is work done with the people that you see here, led by Rohan Gao. Now, we've been looking so far thinking about audio as something the agent hears from a distance. You know, there's some sounding object and it experiences it. Now I want to shift to the flip side where the agent itself is emitting a sound in order to learn about the surrounding environment. So what will happen is the agent's going to emit a sound, and when it does so, then the environment will bring sounds back to it in terms of the echoes. And this is what we want our agent to exploit in order to learn about the geometry of the space. Where are the major surfaces? How are they oriented? Okay, so this is the main idea, and what we're headed towards is a new self-supervised image feature learning approach that is trained based on how an agent can learn the connection between what it sees and what it hears from echoes. So we'll return to the simulator that I described from our work earlier today, and in this now we'll let the source and the receiver be at the same position. So the agent is somewhere in this environment and it emits a sound and also listens to the response at that position. And we'll emit a sweep of frequencies in order to get a rich response from the environment. Furthermore, we record these echoes from the agent's point of view. It moves in a few different orientations. So here we're looking on the left at a top-down view of an apartment. The agent is at that crosshair arrows, and if it looks in a certain direction, say forward, it will see the RGB in depth and receive an accompanying set of echoes, one spectrogram for the left and right ear. And similarly, as it rotates to different orientations at the same position, it will see something different and it will receive these different echoes. Okay, so imagine capturing these kind of paired data between the audio and the visual anywhere in this environment. Now, with that data in mind, I can present the key idea for this approach, which we call VisualEchoes. This is a self-supervised feature learning approach, and we're going to learn a visual representation based on this idea that the echoes carry information about the shape of the scene, meaning the major surfaces, the depth in front of the agent. And so we want to force this representation to capture whether echoes are congruent or incongruent with the current RGB view. So it looks like this. The agent sees something in front of it, and we'll have a visual echo net to process those into features. And then it also hears the binaural echo response. Now, during training, that echo response, we are going to insert, and it's going to be either the correct echo response for the given view or an incorrect one that specifically is taken from any of the other orientations that the agent could face at that position. Okay, so there's 4 possibilities of echoes coming in here, and the task for this network is to be able to take the audio and visual and predict whether that echo response is consistent with the visual input. And so this is a classification problem predicting which of those directions it is. Now, to do this task well, the representation must be able to capture from the RGB whether those aspects of the RGB view that indicate consistency or inconsistency with the shape revealed from the audio echoes. Okay, so that's the idea of why we could self-supervise this. And importantly, once we've done this learning, what we're really interested in is the visual encoding. So during training, we have echoes and we learn from them to make a richer RGB encoder. And then when we're done training, we pull that echoes away, and now we're left with this encoder that we can use to embed this audio learned spatial information into the visual features. And just to give you an example, an NYU data set for depth estimation, here we're applying the model I just described using a state-of-the-art framework where we replace the backbone model with our pre-trained VisualEchoes net. And we get results like the ones you're seeing here that are much better than those you can get just learning from scratch with the same exact model. So that shows you transfer then from replica, the synthetic environment in which we learned, to real-world images in which this visual echo features is having a good impact. And furthermore, we've done this not just for monocular depth prediction, but also for other downstream tasks that can benefit from this pre-trained spatial encoding, like surface normal estimation and visual navigation. And in these cases, what we're seeing is that we're competitive or even better than the supervised, heavily supervised ImageNet or MIT Indoor Scene pre-trained models. Now, just before I close, I want to give a teaser for some work we're doing using audio for efficient activity recognition, and this work appears in the main. The idea is we have untrimmed video as input, and we want to recognize activities. We propose to use the audio stream as an efficient way to preview the content and represent it. In particular, first we show how frame-by-frame processing for a clip can be replaced by instead processing just a single frame and the audio through a cross-modal distillation approach. And then using those representations over time, we show an efficient way to skip between the clips that are needed to get the right label. So to recap where this talk has been, my focus was on the sights and sounds within 3D spaces. And so we're looking at agents that can see and hear for spatial understanding specifically. And I showed three main technical components there. One, the introduction of AudioGoal as a new navigation challenge, plus this simulation platform that will allow reproducible experiments for it. Secondly, I talked about audiovisual waypoints and acoustic memory within an RL-based model to tackle this new challenge. And then I talked about VisualEchoes as a means to learn visual features from audio during training. And finally, I just showed you this teaser for Listen to Look appearing here at the main conference. Thanks so much for your attention, and be really glad to have any questions.